Okay, well, thank you very much for the introduction, and I'd like to thank Professor Johansson for inviting me to give this talk. Actually, I was planning to do this talk last March, and I actually got almost all the way to Stockholm before I was prevented from continuing my journey because of the current pandemic. Anyway, so much delayed, but eventually I'm able to give this talk. So I thought I'd talk about robust adaptive model predictive control. I know that KTH has a long history and quite a lot of people working on adaptive control. So I'm hoping that this is of interest to the audience. So predictive control, as I'm sure most of you know, is an optimization-based strategy where a model of the control system is used to predict the future performance and behavior of the system and optimize a future predictive control sequence. This process is repeated periodically, and it's updated based on the most recent information on the system states in order to obtain a closed loop, a feedback law that's actually applied to the real system. So the process obviously involves a model of the system, and uncertainty in the model and uncertain disturbances affecting the system have a big effect on the performance of the controller. And this means that typically a lot of effort is put into identifying the system model. And this is often done using offline identification processes. But what I want to talk about in this talk is online parameter estimation simultaneously with controlling the system. So the idea is that we want to design a predictive controller that will enable us to identify the model or possibly the costs and constraints to perform a particular task online. And we want to do this while satisfying constraints robustly and while ensuring closed-loop stability and performance guarantees. And finally, we also want to ensure that the parameters that we estimate converge in some sense to the true values. So this type of application of MPC is very common. So whenever you have uncertainty in the system model or in the environment where the system is operating in, you really need to have some kind of online adaptation to update the system model in order that the predictive controller can perform optimally. So a couple of examples here. Firstly, looking at energy management for hybrid electric vehicles, we need to know the future power demand on the vehicle in order to optimize the power split between the different energy sources on board the vehicle. And usually the prediction of the future power demand is very uncertain, even if you know exactly where you're going to go. Things like traffic conditions and the uncertainty due to the route that you might take can affect the prediction of the power demand. So in this case, we need to have a way of updating our predictions of future power demand in an uncertain environment. Another example is with autonomous agents interacting over a network, and particularly if the network is changing over time, so you have new agents entering the network, then the agents need to be able to adjust their control strategy based on the other agents that they're interacting with. So, for example, if you look at the problem of platooning vehicles on a highway, then we need to be able to adjust the control strategy as the vehicles may not know exactly what the other vehicles in the platoon, what their dynamics are, and you may even change the number of vehicles or the coordination within a platoon. So in this talk, I want to discuss some recent developments in adaptive control in this predictive control framework. This is a an idea that has a very long history. So some of the earliest industrial implementations of predictive control, like GPC, for example, were really motivated by the ability to for these algorithms to be self-tuning. But recently, some new tools that have been developed in the context of robust MPC have allowed a kind of resurgence of these techniques, and looking at the design of adaptive controllers from a new perspective. So some of the tools that I'm going to focus on in this talk are set membership estimation methods. So this is instead of identifying a single parameter value, identifying a set of parameters which the plant parameters have to belong to. Having a set of parameters allows us to use robust tube MPC methods to efficiently control the system and to satisfy constraints robustly and to guarantee closed-loop stability. And finally, some recent ideas on how to extend predictive control to the dual control problem, where we want to simultaneously identify the system parameters and perform some kind of control task. So looking at the two of those aspects in particular, in terms of identification of system parameters in online model predictive control, there are various different approaches that have been kind of developed recently. So one of these is to include constraints in the predictive control formulation which guarantee persistence of excitation. And the idea here is that the predictive control is in some senses an ideal framework for doing trying to optimally control the system simultaneously with identifying the system parameters, because given a prediction of the future information that can be obtained from the system, we can balance the costs associated with those two tasks. And so one of the approaches of actually doing this is to introduce constraints which ensure persistence of excitation, which I'll talk about more in a moment, which is a method of basically guaranteeing that there's enough information to identify the system parameters, enough information in the control signal that's applied to the system. Other approaches to ensuring asymptotic identification of parameters are based on Kalman filters, so recursive least square parameter estimation, and incorporating measures of information in the control sequence in the cost. So this is directly trying to balance the information that's available from the control sequence with the cost of actually performing a particular control task. And there are various other approaches that have been looked at recently based on Gaussian processes and particle filtering and so on. The second point here is that we can ensure satisfaction of constraints robustly if we include constraints in the formulation of the predictive controller. So one of the main reasons that predictive control is so widely used currently is that you can incorporate constraints in the formulation of a predictive controller in order to ensure that they are satisfied robustly. So within the context of adaptive predictive control, some various different approaches have been suggested. One of these is to use estimates of the model parameters that are determined online to update the cost that's used to optimize performance. And the reason for updating just the cost is to avoid having to modify the constraints that are used in predictive control. So this type of approach uses a fixed constraint set based on some worst case parameters for the system and only updates the cost. What I wanted to talk about in this talk is the development of an alternative type of approach where a set-based identification method is used to identify a set of parameters, and then robust MPC is implemented based on this parameter set. And so this paper by Tanaskovic in 2014 looked at the case of stable finite impulse response plant models. And some of the work that I'm talking about today is an extension of this to the case of models that are possibly unstable, state space models, and how to guarantee persistency of excitation of the controller. So in this talk, I'll start by describing the set membership parameter estimation that's really key to the application of robust MPC in this context. I'll then briefly talk about a tube robust MPC algorithm that we have developed for use in adaptive MPC. Then I'll discuss persistent excitation, how we can ensure that the closed-loop system will have sufficient information that we can actually asymptotically identify some parameters of the plant. And I'll finish off by talking about extensions to more general parameter estimation methods. Okay, so I'm going to assume that we have a plant model which has an unknown parameter vector theta and is affected by some additive disturbance. So I'm assuming that the model is linear in the states and the inputs. It's a linear unknown system. I'm also going to assume that the model depends affinely on the unknown parameters, the theta star. Okay, so we can rearrange this model to write it as a linear function of theta star, where the capital D and lowercase d here depend on the states and the current state and input to the system. I'm also going to assume that the disturbance is stochastic, but it belongs to some disturbance set W, which we know. So I'm going to assume that this disturbance set is compact and convex, and I'll talk in a few minutes about how we can relax some of these assumptions on this W set. So set-based parameter estimation methods are derived from an unfalsified set of parameters. So suppose for the moment we can measure the system states. So at time k, based on the current state and the previous state and the previous control input, we can define a set for the parameters which is unfalsified, in the sense that if the theta parameter doesn't belong to the set, then we know that it can't satisfy this system model. Okay, so based on this unfalsified parameter set, we can update our estimate of the actual parameter set just by taking the intersection of our best current estimate with the unfalsified set. So I'm going to start by talking about a parameter identification scheme where we define the new parameter set as just the intersection of the old parameter set with the unfalsified set. So a couple more assumptions I want to make here. First of all, the disturbance set W is a tight bound, in the sense that given any point on the boundary of this disturbance set, there is a non-zero probability of a realization of the disturbance being arbitrarily close to that point on the boundary. So for every point on the boundary, there's a non-zero probability that a realization will actually be arbitrarily close to that point on the boundary. And the fourth assumption here is persistent excitation. So this basically requires that the regressor in the system model, that's the matrix which multiplies the unknown system parameters in order to give us the quantity that we can measure. In this case, I'm assuming we can measure the state. This regressor has to satisfy these properties. As first of all, it has to be bounded for all time steps k, and secondly, it needs to satisfy this rank property. So for every time step k, I'm requiring that there is some time interval n. So this is like a window of time steps over which the regressor satisfies this positive semi-definite condition. Sorry, this is a positive definite condition, so only beta greater than 0. Okay, so based on those four assumptions, we can guarantee that the parameter set is identified using just by taking the intersection of the unfalsified set with the current estimate of the parameter set. We can guarantee that parameter set converges in a probabilistic sense to the true parameters. And just very briefly, the way that this analysis works is that if we have a realization of the disturbance which lies on the boundary of the disturbance set, then we can immediately define a hyperplane which passes through the boundary, or is tangent to the boundary at this the value of the disturbance, such that whenever this vector lies on this side of the hyperplane, we can exclude that from being, we can exclude all the corresponding values of theta from belonging to the actual parameter set. So this gives us a whole half space that we can exclude from our estimate of the parameter set. We can make this a bit more, we can make a slightly more useful statement if we assume that instead of the disturbance realization lying on the boundary, it just lies sufficiently close to the boundary. So if we have a particular value for this vector, and we can pick a point on the boundary of the disturbance set such that the normal to the boundary at that point is parallel to the vector that we're interested in. And then whenever the disturbance realization is sufficiently close to that point on the boundary, we can guarantee that the theta naught, the kind of test parameter, doesn't belong to the current unfalsified set. Okay, so this leads us to some nice conclusions about the convergence of the parameter set estimate. So if we have these four assumptions, that's basically that the disturbance belongs to a convex compact set, that the model is affine in the parameters, that the disturbance set is tight in the sense that the realizations of the disturbance can approach the boundary with non-zero probability, and finally we have persistence of excitation. So under those four assumptions, we can show that we have convergence to the true parameters assumed to be, for now, we're assuming them to be time invariant. And this is asymptotic convergence with probability 1. And the reason for this is basically we can get a bound on the probability that any given parameter value that's greater than a certain distance from the true parameters, we can bound the probability that this doesn't belong to the unfalsified set, and on any time interval of n time steps, where n is the window that was used to define the persistence of excitation condition. Then based on this probability, we can get a bound on the probability that any given parameter value doesn't belong to the parameter set estimate after k time steps, whenever this parameter estimate is greater than a certain distance away from the true system parameters. And you'll notice here that as k tends to infinity, the quantity on the right-hand side here tends to 0, so we get a convergence in probability type of result. And we can tighten this up using the Borel-Cantelli lemma to show that with probability 1, any parameter vector that's not actually equal to the true parameter vector will be excluded from the parameter set estimate. So I wanted to show this result because I wanted to point out that the convergence here increases, the convergence rate increases as the value of beta increases, and beta is what defines the measure of persistence of excitation here. So for example, applying this to a particular problem, the first 6 time steps, the parameter set is shrinking across as we go across these two rows, and as time advances, we're basically taking the intersection of our parameter set with, in this case, the polytopic set. So we're adding more and more hyperplanes to the parameter set description. So this could be a problem because it means that the number of hyperplanes that define the parameter set is potentially growing without bound. But we can refine the scheme by using a fixed complexity polytopic set if we define the parameter set as being expressed in this form, where the matrix h theta here is fixed, and in order to update the parameter set, we're updating the right-hand sides of these linear inequalities that define this polytopic set. Then, in order to update the set, we basically calculate the right-hand sides of the linear constraints, which ensure that the set is always shrinking at each time step, and also compute gives us the minimum volume parameter set update that contains the old parameter set and the intersection with the unfalsified set. So here, in order to speed up convergence, I'm assuming that we're going to apply the parameter set update using the last n time steps of data. Okay, so this is actually using an update based not just on one time step, but on a window, where the number of elements in the window here, the number of time steps n, is the same as the number that we use to define the persistence of excitation condition. Okay, so again, under the 4 assumptions that I mentioned on the disturbance, we can guarantee that the parameter set also converges to the true parameter estimate with probability 1 asymptotically. So, and the arguments follow a similar kind of approach to what I just presented previously. And again, I wanted to point out here that the rate of convergence, the probabilistic rate of convergence, increases as beta increases, where again beta is the quantity which defines the persistence of excitation on the input-output data that we have for this system. Okay, so again, another example showing you how this works in practice. This is a low complexity, fixed complexity parameter set. In this case, it's just a hyperrectangle, and you can see how the volume is decreasing over time. And the interesting thing to note here is that we get quite quickly to a much smaller volume. So after 10 steps, we've reduced the volume by 90% or so. It takes a very long time to get to a very small parameter set. And that's basically because of the way that we are updating the parameter set here using the intersection with the unfalsified set. A final point to note here is that these values in this column here are the optimal values for the MPC costs. So here I'm using a robust MPC algorithm based on the this parameter set volume, but I'm just fixing the parameter set now and calculating the cost starting from some fixed initial conditions. So you can see the effects here of improving the parameter set estimate, and obviously we're getting a reduction in cost. And it's interesting to note that there's still a cost reduction going from a very small parameter set to the exact value of the system parameters. And that's basically because of the inherent conservativeness in the robust MPC schemes that we're using here. So how can we relax a few of the assumptions on the disturbances? So first of all, supposing we don't know the bounding set for the disturbance exactly, and this is quite common in practice, but supposing we have an estimate of the set that the disturbance lies in, and supposing we also know that that estimate is no more than a factor rho inaccurate. So let's suppose that we have this condition that the actual disturbance set plus, our estimate is contained in the actual disturbance set plus rho times a ball radius spline. Then if we replace the disturbance set with our estimate in the definition of the unfalsified parameter set, we can again get, we can guarantee convergence to convergence with probability 1 to a neighborhood of the optimal parameters. And here that the neighborhood depends on the accuracy to which we know the actual disturbance set. So the rho appears here. And also beta appears again, so if beta is greater, if beta is bigger, then we can get a more accurate bound on the asymptotic value of the parameter set. A final refinement I wanted to mention is that supposing we can't measure the state exactly, but we have some noisy measurement, then provided we have some assumptions on this noise, so for example, the noise belongs to a complex polytopic set, and if this noise band is tight, in a similar way to the tightness assumption we made on the disturbance, then we can again guarantee convergence of the parameter set to a neighborhood of the actual parameters. This is obviously quite useful in practice because often you'll be using a state estimate rather than an actual state. And provided we have bounds on the state estimate error, then we can use this type of analysis to show that our set-based parameter estimate will actually converge to something to a small neighborhood of the actual system parameters. Okay, so in the definition of a predictive controller, I want to combine this parameter set estimate with a point-wise parameter estimate. And there are various ways of defining this, but I want to focus initially on a least mean square filter method. So we use an LMS filter to determine an updated point estimate based on our current point estimate and the current state measurement, and then we combine this with the parameter set that we've developed using this set-based parameter identification method by simply projecting this estimate onto this set. So we take the closest theta within our current parameter set estimate to this recursively least squares estimate, and we use that to define our current point estimate. Okay, so this LMS filter has a nice property that it guarantees a finite L2 gain bound on the one-step ahead prediction error. So provided we can guarantee boundedness of the states and the inputs, then we can also show that the sum of one-step ahead prediction errors is bounded by a function of the sum of the norms of the disturbances and the initial parameter error. And this is useful when you're looking at the stability of an MPC scheme based on this point-wise parameter estimate. So coming now to the control problem, suppose we want to regulate the system subject to some constraints. I'm going to assume these are just general state and input constraints, but I'm assuming that they are linear. And I'm going to very briefly discuss a possible robust MPC scheme which uses the point estimate and the parameter set estimate. I don't want to go too much into the detail of this. If you're interested, have a look at our paper in the International Journal of Robust and Nonlinear Control from this year. But basically, we can combine these same ideas with virtually any robust tube MPC approach, which gives us an input to state stability guarantee. So here I'm going to assume that the system is stabilizable in the sense that there exists some set which we can ensure is robustly contractive under some linear feedback gain. Okay, so this is an assumption. This assumption allows us to define a tube MPC method based on that set to define the cross sections of the state tubes, which I'll explain in a moment. So some of the notation here. So the predicted states and inputs I steps ahead are written using this dual notation. So this is the predicted state I steps ahead prediction being made at time k. And I'm going to assume that the free variables in the control sequence are added to this linear feedback control over the entire prediction horizon. But we set these equal to 0 after a finite horizon of n steps. So this is the usual method of converting an infinite dimensional control problem into a finite dimensional control problem in receding horizon control by explicitly predicting the first n future control inputs and then relying for the subsequent infinite horizon relying on a terminal feedback law which is designed offline. Okay, so the performance index here is defined in terms of this point parameter estimate, and we can define a set of robust constraints based on a tube which bounds the predicted sequences of states for all the possible uncertainty that's parameterized by our uncertain set, our set of that contains the current parameter estimate. So in this setup, we're going to use polytopic tubes. So the tube is a sequence of of polytopic sets defined by the intersection of linear inequalities. And these are flexible in the sense that online we're going to optimize the right-hand sides of these inequalities. This allows us to change the shape of the predicted state tube. And this is important, actually, particularly for adaptive MPC, because it means that we can optimize the terminal set that's used in model predictive control online based on our best current estimate of the parameter set. Okay, so I'm not going to go through the details here, but basically we're using a robust tube MPC method with a polytopic tube description. We're using both the hyperplane and vertex description of the sets which define the tube. Okay, so the constraints that we get for this MPC scheme are linear, and I'm going to define the feasible set as so the feasible set in terms of the decision variables. So that's the sequence of perturbations that we apply to the linear feedback law, the sequence of parameters which define the robust tube, and another set of parameters which define the effectively these are slack variables in the definition of the robust constraints. So the feasible set for these parameters is defined as this set F. Then the online MPC algorithm involves at every time step first updating the parameter estimate, so the set estimate and the point estimate, then solving the MPC optimization, which optimizes this nominal predicted cost subject to the robust constraints. And because of the formulation here with linear system, quadratic cost, linear constraints, this is a QP, a quadratic programming problem. So this has some nice properties. First of all, it has the property that the parameter set estimate will always contain the true parameters. And secondly, the MPC scheme is recursively feasible. So if it's initially feasible, it will remain feasible for all time. And then thirdly, the constraints will be satisfied robustly by the closed-loop system. We can also say that given the properties of the RLS point estimate for the parameters, we end up with a finite gain L2 stability condition. So that means that the norm of the regulation area here depends on the two norm of the disturbance sequence. Even if we go for a much simpler point estimate update rule, so here if I set the parameter mu in the RLS algorithm to 0, we end up with a point estimate which is simply projecting the previous point estimate onto our current parameter set estimate. And in this case, so this is possibly the simplest point estimate that we could use. In this case, we can still guarantee input to state stability of the closed-loop system in the sense that the norm of the state is bounded by a function of the worst case disturbance over time. Okay, so just to show you how this works in practice, this is a very simple example. So a second order system, we have an initial parameter set estimate and a uniformly distributed disturbance on the disturbance set, and some state and input constraints. So here you can see how the tube for the states, the predicted tube for the states at initial time evolves over time. So as I mentioned earlier, the shapes of these tube cross-sections are actually variable and optimized online. And in red, you can see the closed-loop trajectory for the actual system given a particular disturbance realization. So how this algorithm works in practice, if we give it a set of references to follow, you can see in this plot, in the dashed red line is just the robust MPC method with no parameter adaptation. So the parameter set is just fixed at the initial value, and in blue you can see what happens if we update the parameter set online. We get slightly faster convergence, less overshoot over time. Okay, so so far I've assumed that the parameters that we're trying to estimate are fixed. we can extend this type of approach to the case where the parameters are actually slowly varying over time. And by slowly varying, I mean the change in the parameter value is bounded by some number, which I'm assuming is known. So there's some radius, maximum radius, which limits the distance of the consecutive values of the true parameters of the plant. So based on this this rate restriction, we can define a dilation operator, which basically just expands the parameter set estimate at a rate dependent on this this rate limit. Then, using the parameter set and the dilation operator, using the unfalsified parameter set, we can actually define the update for the parameter set estimate in a similar way to what we had before, but we just expand the unfalsified set before we use it to define the updated set. And here we've also used the dilation operator to bound the evolution of the parameter set estimate over the prediction horizon, and this allows us to define robust constraints for the system in the MPC optimization problem. So again, this strategy has a guarantee of recursive feasibility and constraint satisfaction, but in this case we can't guarantee the L2 stability property because of the extra time varying tracking error that we get from the parameter variation. It's worth noting that if the parameter set, if the true parameters are time varying, then the parameter set can both shrink and grow. And you can see that here in this example. The parameter set is initially shrinking, but then it grows and then it shrinks again. And comparing this with what would happen if we had fixed parameters, you can see that in that case the parameter set would actually monotonically be shrinking. Okay, so I mentioned at the beginning that one of the key properties of adaptive model predictive control is that we can ensure persistence of excitation just by optimizing our predictive control sequence to guarantee that some PE condition is met. So the difficulty here is that the persistence of excitation condition is actually a non-convex constraint on the optimization variables in the MPC formulation. And that's basically because the regressor here depends linearly on the optimization variables. So this represents a lower bound on a quadratic function, which gives us non-convexity. But if we have an estimate of the optimal sequence of controls and states, then we can linearize around that estimate. And in fact, it's possible to linearize this in a way that gives a linear condition which is sufficient to guarantee the original condition. So it's not necessarily approximate. Well, it's approximate, but it does actually guarantee sufficient conditions for persistency of excitation. And the idea is that if we linearize around a reference trajectory and neglect the quadratic term in the expansion that we get, then we get a linearized condition that needs to be satisfied to guarantee the PE condition. And we can express this as an LMI on the optimization variables that define the MPC scheme. And so basically this leaves us with a linear matrix inequality to include in the MPC optimization problem in order to guarantee persistence of excitation with any given measure of beta. So the optimization that we could solve, if we're solving this as a multi-objective problem, where we want to balance the cost of identification with the cost of tracking or regulation of the model, then we can update the scheme like this. So basically, we have the updates for the parameter set estimate and point estimate, and then we solve an MPC optimization problem, which is the same as what we had before, but now I've included a penalty on the persistence of excitation measure beta, and we've also included the LMI constraints. So this is now a semi-definite program rather than a quadratic program. So some immediate problems that arise from this approach. First of all, how do we choose the gamma which determines the trade-off between tracking and persistence of excitation? Secondly, can we guarantee stability? So basically, by introducing gamma into the cost here, we can no longer use input to state stability analysis to guarantee closed loop stability. And thirdly, can we even guarantee that the closed loop system is persistently exciting? So can we guarantee that beta will always be greater than 0 with an optimization problem like this? So the next few slides, I want to talk about how we address these problems. Basically, we can do it by using a standard approach in MPC, which is to use the properties of the terminal predicted feedback law, so the linear feedback law that we're assuming applies after a finite number of time steps to predictions. We can use the properties of that terminal feedback law to ensure some properties for the entire, or the solution of the MPC optimization problem. So the idea here is that if we apply this linear terminal feedback law, then because the regressor is a linear function of the states, we can get a bound on the persistence of excitation measure within the given this linear feedback law based on the properties of the disturbance. So if the disturbance sequence is has a covariance matrix which is minimum eigenvalue greater than 0, so bound by this epsilon W quantity, and if we also have a condition on the system dynamics, which basically means that the parameter vector which defines the state sequence is unique. So basically, the minimum singular value of this matrix is positive. Then we can guarantee that the persistency of excitation condition is actually satisfied under the terminal unconstrained feedback law. Then in the MPC algorithm, we can define a set of windows over which we impose persistency of excitation constraints. Okay, so this set of windows goes from the furthest, so the window furthest into the future actually is contained entirely in the time interval where we're applying the terminal feedback law. But then we have one window per time step all the way back to current time. So this window, this earliest window, extends into the past and contains a single time step, which depends on the current control. Then the idea is that by having this sequence of windows, we can guarantee that the properties of persistence of excitation, which hold for the terminal feedback law, are actually propagated back through each of these windows and applied to the closed loop system. So this is the modified algorithm. So I basically inserted an extra step here. So in this step, what we're doing is we're calculating a lower bound on the PE, the persistence of excitation measure, for each of those constraint windows. And this lower bound is calculated so that it's the maximum that we can guarantee will be feasible given the solution from the previous time step. So this is based on the solution for the state tube and the control sequence that was calculated at the previous time step. In order to calculate these bounds, we need to solve a set of semi-definite programming problems, basically one problem per time step of the end step prediction horizon. Then the MPC optimization problem becomes this. So basically, we're minimizing the nominal predicted cost subject to the robust constraints and the LMI relaxation of the PE constraints, which use now the maximum feasible, or the bounds on the feasible right-hand side of the constraints that we calculated in step 2. And this can actually guarantee closed loop system will satisfy a PE condition. And the reason for this is that if we think about the solution of the MPC optimization problem at time t, so for the window which applies n steps ahead, so it's entirely contained in the time steps where we're using the linear terminal feedback law. If we compare the value of beta for this window with what we get one step in the future, so we advance time by one step, consider the same window, then the way that the bound on the persistence of excitation constraint was defined for this window means that the solution for beta corresponding to this window has to be greater than the value that we had at time t. And we can reapply this argument for n plus np steps until we get to this situation where now the prediction horizon extends all the way into the future beyond this time step. And so because this window contains past values and just one current, one time step which corresponds to the current control input, the solution of the MPC optimization problem for beta will actually be the persistence of excitation measure that's experienced by the closed-loop system for this particular window. So given the monotonicity properties of these beta values, we can set up a load of inequalities like this. And if we take the expectation of each of these inequalities, we end up with a bound on the closed loop value of expected beta. So the closed loop properties are, again, we have recursive feasibility and robust constraint satisfaction. We can now guarantee that the closed loop system is input to state stable because we've removed the term. Remember, we had that minus gamma times beta, which was messing up the ISS analysis when we had a multi-objective problem. And we can also guarantee this closed loop persistency of excitation constraint. So looking at an example, this is an example from the paper by Marifiotti from 2014. Here we're taking the PE window to be of length 3 and the mode 1 prediction horizon for MPC to be 25 steps. So these are the mean and the range of the values of beta for 30 disturbance sequences for the closed loop system. And in blue is the algorithm with the PE constraints, and in red it's without the PE constraints. And if we look at a longer simulation horizon, so here 500 steps, you can see that the PE constraints are making a significant difference to the closed loop value of beta. And actually the value that we're getting here is close to the bound that we can obtain using the terminal feedback law. You can see here the effects of having a larger value beta. So without the PE constraints, the parameter set for this example is not converging to the true system parameters, but with the PE constraint we get an asymptotic convergence in probability to the true values. And the price that we pay for this improved identification scheme is basically increased computation. And you can see that the extra step that was required to calculate the feasible bounds on the PE constraints that we used is taking quite a significant fraction of the total time required to implement this controller. So I wanted to finish in the last 5 minutes by talking about more general schemes for estimating the system parameters. And I'm focusing now on the point parameter estimate. So instead of using a recursive least square estimate, can we use more general stochastic gradient descent type methods for estimating the point estimate, and combine this with a parameter set estimate? So one way of doing this is to consider the MPC law as the solution of a multiparametric programming problem, where if we can calculate if we can examine the optimality conditions, we can work out how the optimal solution will depend on as we perturb the parameter estimate. Okay, so this allows us to use gradient descent type methods to train our parameter estimate. So, for example, we could define the parameter estimates using a recurrent neural network, and we can use gradient descent to actually train that network in order to optimize performance or to optimize some kind of measure of loss. So in this type of scheme, what we're doing is we're combining the MPC optimization as a layer of a neural network. And we want to keep the parameter set estimate in the way that the the theta hat is updated in order to prevent theta hat from actually straying outside our parameter set estimate. Okay, so an application of this to an imitation learning problem. Suppose we have a system model which is linearly parameterized in our unknown parameter vector theta star, and given this linear parameterization, we can use the method that I described earlier for updating the parameter set estimate based on the unfalsified set, and we can identify the point parameter estimate using a backpropagation type scheme, but projecting the gradients that we get into our parameter set estimate in order to ensure that the point estimate is consistent with the bounds that we get from the observed evolution of the states. So, for example, an imitation learning problem involves trying to learn the parameters of the model, or possibly the cost that we're using in MPC, in order that the distance of the controller from some expert controller is minimized. Okay, so we have an observation of an expert controller, and we want to define the system parameters so that the MPC controller matches this expert controller by minimizing this quadratic cost. This is a very simple application of this problem to a control of a sprung mass. So we have a mass, a spring, and a damper. Here we don't know the system parameters, so the K, the C, and the M, and the controller is the force that's being applied to the mass. And you can see how these plots relate to training the neural network parameters for different horizon lengths and with different types of model. And it turns out that if the damping here is lower, then it's easier to get faster convergence of the parameter estimates. And that's basically because there's more information on the parameters in the system response. So there are various difficulties with this type of approach. So first of all, it's inherently non-convex, so the minimization of the loss function results in non-unique optimal parameters. Another problem is that you have to be very careful about how you apply the predictive controller in this type of approach, because the gradient information, the sensitivity of the controller to the parameters can be lost if you have a long prediction horizon. And then a key point here is that the expert controller may not be persistently exciting. So this is a motivation for trying to introduce persistency of excitation constraints into the predictive controller. So I want to finish with a slightly more interesting example. This is a platooning problem where we have a set of n vehicles with some initial spacing between them and initial velocities. We want to control the vehicles so that they settle to a fixed spacing between them. I'm assuming that we know the system model, but we want to learn the MPC cost, which corresponds to a particular expert controller. And so we applied this for 10 vehicles, and we optimized the quadratic cost weights in a robust linear MPC scheme. And we found that we could get the ideal constrained LQ performance with 20 time steps in our prediction horizon. Okay, so to conclude, I've been talking about adaptive, robust MPC, and I wanted to stress that this problem is computationally tractable for systems where the dynamics are linear and they depend linearly on the unknown parameters. I talked about how to combine set membership parameter estimation with robust tube MPC to guarantee constraints. The constraints can be satisfied robustly despite identifying system parameters online. And I talked about how to guarantee parameter convergence in probability by including extra constraints in the MPC formulation. So some questions that are of interest is, how can we avoid this assumption that the disturbances are bounded? So can we use, for example, sets that apply with a given confidence to distributions which maybe have unbounded support. How can we combine persistency of excitation with recurrent neural network model adaptation? And I'd like to thank Xiaonan Liu, Sebastian East, and Matthias Lorenzen for their work on this aspect. So are there any questions?